an alloy containing 70% of nickel and 30% of copper at 150, but make phase analysis assuming equivalent conditions. Okay, in the phase analysis include the following. You have to determine the phase. Okay, the liquid, solid or liquid plus solid. Chemical compositions. What is composition of the phase that you already identify? Amount of each phase. Okay, this is by using the level rules. Okay, okay. And then make a similar phase analysis at 1500 degrees C. Okay, you have to uh, uh, determine whether it is a liquid, solid alpha, or liquid plus solid alpha. Okay, sketch the process of the alloy and at each of this temperature by using circular microscopy. Okay, so this is the diagram lah. Okay, so it stated that you have to determine the phase, right? Okay, so what do you think? This one, since it's 1500 and we start with 30% of copper. Okay, so this one is gonna be what? And 30% of copper, 100%. This one lah. 13 plus 0, yes, it's liquid and solid. Just nice. Liquid plus solid. Okay, so L plus this one, right? Okay, so L plus alpha. Okay, thank you very much. Okay, and then number 2, what is the chemical composition? So if you look at here, okay, this one. How many percent? And another one. How many percent? How many percent of nickel? How many percent of copper? Okay. So here you can see, right? Okay. Look at here. This one is around 74% weight percent of nickel lah. And the rest is 28 weight percent of copper. Right. Okay. And then here around how many percent? 62 weight percent of nickels. Okay, and then the rest is around 38 weight percent is copper. Okay, so that is the composition. Okay, so now we want to calculate the percent of solid and liquid. Okay, so from the equations, if you still remember, okay, level rules equation. What is the level rule equations? So for the liquid phase, right, XL, okay, equal to WS minus W naught divided by WS minus WL. Okay, so WS is a solid. Solid is about this one 74%. Okay, 74% minus W naught. This one 70. Right, this one is W naught. This one is WS. And this one is WL. L. Okay, can you calculate this one? 70 divided by, what is it? 70 minus 62. Okay, time 100%. Okay, thank you. 33.3%. You can see in the chat box the answer. Okay. No need to send privately. Okay, just send to everyone. Okay, send to everyone. Okay, you have to share with your friend. No need to send privately the answer. Okay, so the answer is 33.3%. And the rest, 100 minus 33.3 is equal to this one, 66.67%. Or you use a equation of WS. Okay, WS. This one, W naught minus WL divided by WS minus WL. Okay, so you know how to calculate. How about 1500 degree C? Okay, so this one done, okay? One 500 degree C. Okay, 70 and then 1500. So what phase here? This is 100% liquid. Okay, 100% liquid lah. Okay, so how to draw the microstructure? Okay, so if you look at here that sketch the microstructure of alloy at each of this temperature by using circular microscopic field. Okay, so at 1500, how you draw? Maybe sometimes I say use the 20 cents of size or 50 cent size, right? So you just draw. This one is liquid, right? Okay, and then another one is this one, just this nice. Okay, so like this one. Okay, so this one is 1500 degrees C. So 1350. Right? So 100% fit lah. Okay. And then this one you have to draw like this lah, to show that there's a, what is it? The solid. Okay. So this is a solid alpha phase. This one is solid. And this one is liquid phase lah. Okay. Okay. So easy right? So that's all the answer. Okay. Okay, this one similarly also for the copper nickel phase diagram in the below, find the composition of the liquid and solid phase for nominal composition of 60% nickel and 40% copper, 1316. Right, so this is around here. This is 126. What else? This is 1300. Maybe just nicely here lah. Okay, 2400 degree Fahrenheit here. Okay, it's stated already. 1000 degree Fahrenheit. And then how many percent? 60% nickel. Okay. So this one is also liquid plus uh, liquid plus alpha lah. Okay. Use lever rule to determine the proportion of liquid and solid phase. This one lah in the alloy. Okay, if you look at here, it starts here, right? This is WL, and this one is W. WS lah. Okay. This one is WS, W not WL. Okay. Because this one is touch, the liquid is line. This one is touch, solid is line. That one WS. Okay. So just using WL equation and XWL, XL and XS. So you can get the answer. Okay. I have no answer actually for this one, but that is the solution. What is the answer? You can calculate. Can you calculate? Of course, this one is the answer number one is a liquid plus alpha. This one WL S minus W naught divided by W S minus WL. Okay, and then 100 minus X. So you can get answer. Okay, what is the answer? Can you find the answer? Give me the answer. Give me the answer. Apa dia? Oh, kejap. Find the answer first. I want to move my motorbike. Okay, thank you very much. Uh, yeah, the answer is maybe 62%. Okay, 63%. So I think you already have a clear view how to calculate the what is it XL X by using a level rules and determine the composition of nickel and copper, right? And also determine the phase lah. Okay, whether liquid, two phase or solid. Okay, now we move to the next part. Okay, phase eutectic. Okay, so this one uh, is more to limited solid solubility lah. Okay, based on the Hume-Rotary rules. Okay, so based on Hume-Rotary rules, the solubility is not 100%. Okay, not complete soluble. Okay, so in a binary alloy system, we can say that component have a limited solid solubility lah in each phase. Okay, so for example, so we get here that uh, plumbum and also sternum, lead or sternum. Okay, this one is for solder. Okay, if you know the solder is really like flexible, right? So you just can how to say uh, uh, use for the what is it apa panggil battery kan for the electricity lah, like electrical part. Okay, and then another one is copper and also mercury, argentum is mercury, right? Okay, no, argentum, mercury. This one is copper and argentum lah. Okay, this one in candelabra. Okay, um, general diagram for the phase eutectic, actually they have a three phase. Okay, since we mix between two metals. Okay, so they have a three phases. Okay, so if you look at here that three single phase diagrams. Okay, we can see here that on the left side is the alpha solid phase, right? Okay, and this one is a beta solid phase, and this one is liquid. Okay, and this one is actually alpha plus beta. Okay, this one is liquid plus beta, and this one alpha plus liquid. Okay, so if you look at here, okay, A is a this one is a rich solution, solid solution. B is going to be solute lah. A is going to be host. Okay, similar like a copper and nickel, right? Okay, this side is a 100% copper. This one is 100% of nickel. Okay, that is 100% solubility, right? And this one is B rich lah, solution. A as a solute. Still have a A because it's not 100% of how to say, not 100% of solubility, right? Okay, and then this one two phase, alpha plus L, L plus beta, and alpha plus beta lah. Okay, yeah, wait kejap wait. Yes, sorry. Region designated as a alpha phase and beta phase, as it ends, we call it a terminal solution. Here, this one. Okay. This one at the end. Okay, reach with the alpha and beta. This one is for the solid. Okay, and then this one we have the solid use. Okay, this one is liquid use. Okay, because this one liquid, right? This one is liquid use. This one is solid use. Okay, and this one also solid use because beta is solid use. Okay, so until this line. Okay, and then this one is solvus. Okay, this one is solvus. Okay, alpha plus beta. Solvers lah. How to write solvers. Yang ni solidus lah. Liquidus. Okay. So we call it this one a phase boundary lah. Okay. Okay. So this one. Okay. Liquidus, solidus, solvus. Okay, solvus or solidus lah. The phase boundary below isothermal liquid plus proeutectic solid phase. This one. There's a proeutectic. Later I will show you the proeutectic lah. Okay, there's a proeutectic is a primary solid formation. Okay, and then phase boundary is separating terminal solid solution from two phase region of the solid solution. This one is the boundary. Okay, solvers is shows the maximum solid solubility of solid in solution. This one. Okay, meaning that this one if you look at that, okay, this one is A as a solute, right? A as a solute here. Okay, and B is a solvent, a host lah. We cannot say as a solvent. We can say as a host. Okay, this is the solubility of A as a solute in B. Okay, but this one, A as a host, okay, B as a solute, meaning that B solubilized in A lah. Okay, so there's a B in A. So just a maximum the solid solubility because it's not 100%. Okay. Okay. And then we have eutectic compositions. We call it as a eutectic point. Okay, if you look at here that this is a eutectic point. Okay, this is a eutectic point. Okay. So at this one we have eutectic composition freeze at lower temperature than all other alloy composition. Okay, eutectic temperature is the lowest temperature at which the liquid phase can exist, meaning that from here, okay, or from there. Okay. Okay, so from liquid is like you want to solidify it or you want to make the solid melting, right? So this is like a triple point. Okay. Okay. So this eutectic composition and eutectic temperature, we call it as eutectic point. Okay. So that is the definition. Okay. So eutectic point is actually due to the eutectic reaction. So from if you cooling, okay, okay, at this eutectic temperature to the eutectic temperature, okay, from the liquid it's gonna form solid alpha and also solid beta. Okay, this is what we call it as eutectic reaction. Okay, so when the liquid of eutectic composition is slowly cooled to eutectic temperature, okay, the single liquid phase transform into solid phase. This one. See, this is a single liquid phase, right? So it's transformed to A plus B, meaning that liquid to solid alpha and solid beta. This is what we call it as eutectic reaction. And you try to cooling. Okay, there were two solid lah. So here actually, if you draw the microscopic structure, okay, there's going to be alpha and beta. Okay, so there's going to be later I'll show you this one. There's alpha, beta, maybe this one alpha, right? And then there's a proeutectic. Okay, so and then there's another one is a beta, right? So beta, and this one maybe beta. Okay, it's a mixture. Alpha and beta. Blue is beta, red is alpha, and then I also have a proeutectic, which is the first solid is going to form during the cooling. Okay. Okay. The eutectic reactions is we call it also invariant reactions because it occur under equilibrium conditions. The degree of freedom is 0. Okay, similarly like a triple point for the general diagrams previously, just like water, right? They have a 0 degree of freedom. Okay, at 3 points, right? And eutectic point, 3 phases are in equilibriums. If you look at there, a liquid and solid, two solid phases in equilibriums. Okay, these 3 phases in equilibriums. Okay. Okay, for the binary eutectic alloy system, we mostly will discuss on the copper and argentum and also platinum and stannum. Okay, for this. for this topic. Okay, but there's other metals. Okay, we can find. Okay, so for this one, for the copper and argentum is characterized by the limited solid solubility of each terminal phase, alpha and beta. Okay, this one. This one. Right. The most important feature of the system is the eutectic variance. This one. Okay, if you draw this one, okay, this one, 71.9. This is already we call it as the real data. Okay, for the argentum and sternum. Okay, 71.9% argentum. Right, this one. Because look at here. Right. This one is 70. This one is 71.9. So meaning that to that side is 100% of argentum, meaning 71.9 argentum, and the rest 29.1 is copper at 779 degrees C. This one 779. Yeah. At eutectic point, okay, 8% of argentum. How can we get this 8% of argentum? Okay, so since you draw this tie line, okay, we just make it vertical line. Okay, so if you do a vertical line, this one, oh, sorry. Right, this one. So you can see here that 8.0, this one, here. This one is around 10 lah. Okay, and another one is here lah. Right. Okay, this one. So if you look at here, this is alpha here, and another one is 91.2 is here. Okay, and liquid, liquid here lah. This is liquid. Okay, at eutectic point. Okay, similarly, do the blend of the 0.0 into and the rest is copper, beta, 91.2% argentum, and the rest is a copper and liquid, 71.9 argentum, and the rest is copper. Okay, so just minus lah this one, 100%. Okay, so you can get all this composition. Okay, okay, is it clear? Clear? Any questions about this eutectic? Is it right? Okay, clear. This one eutectic isotope lah, because it's what is it? Temperature is constant, right? This one this vertical line. Okay. Okay, for the plumbum and sternum, similarly, just as similar but different data lah. Okay, for the different data, if you look at here, that this is the eutectic point, right? 61.9, liquid of course 61.9, and then for the what is it? Alpha, right? Alpha we have a 19.2, this one. Okay, and then lead 100%, and sternums for the liquid. This one lead lah. Sternum, all this one is for sternum lah. Okay, and the rest is going to be 100% minus this the composition of the sternum. So we can get the for the lead. Okay, okay, okay. So is it right? Okay. Okay. So if you look at here that binary eutectic alloy system for the lead and sternum, alpha phase is lead rich. Okay, this one solid solution alpha phase, this one of course, because if you look at here, all this one is rich with the lead, okay, or plumbum. At 180 degrees C, a maximum 19.2% of sternum. Okay, this one. This one. Okay. Okay, how about beta, right? The right side, beta phase. Similarly, is we just identify at the eutectic point. This one beta, okay, 97.5 lead. Okay, sternum, and the rest is 2.5% lead. Since 100 minus 97.15. Okay. 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 So when we do this cooling, okay, sometimes we can see we can observe. Of course, we have to observe the microstructure. So if you look at here, that this one, right? Okay, this one, this is liquid 100%. But here is, look at here that there's a alpha and beta. Okay. Generally, this one, for the alpha, we use a blue color. This one sternum is like a color. Okay. So meaning that they have a two phase already solidified. Okay. So liquid solidified by eutectic reaction into two phase. Okay, alpha and beta. 19.2% of sternum, and beta 97.5% of sternum. Okay. And further cooling from TE to room temperature, meaning that to this one, room temperature, right? So room temperature may be here. Okay. Solid solubility of solute in alpha and beta phase decrease, as indicated by solvers line. This one also. Okay. This one solvers line. Okay. Can you see this one? Is decreased. Okay. The solubility. This is solvers line. Okay. Okay. So when we do the what is it? When we do the slow cooling for the lead and also sternums, we can see a different angle, right? For this figure, for this point. Okay, we want to see the different angle. Okay, for different angles. Okay, this one is maybe 2D, and this is temperature versus composition. How about we see a temperature versus time, a different angle? How can we see this graph, right? So if you look at here, that this one, when we see from the different angles, right? Temperature versus time. Okay, this is 245, 180 degrees. This one is the isothermal for the eutectic point, right? So from this one, we can say that this is the first solid form, right? First solid form, meaning that 245 here lah, B, point B. Okay, this is first solid, meaning that it's a primary. This one, okay? This one, another one, this side. This one is point, they have point, what example lah? A, this one is B. And then here is around here is a C, this one is D and E lah. Okay, because this one is eutectic point, right? We can see from the different angle. So this is the first solid form. We call it as pro-eutectic or primary alpha. When you solidify, it's the first solid golden form. So if you draw the microstructure, okay, if you draw the microstructure here, right, here, okay, almost here, right. So it's the microstructure is going to be in general lah, macam dot because it's just a primary. Okay, phase pro-eutectic. Okay, we call it as pro-eutectic. Okay, and then it's going to be grow lah when we reduce the temperature. Okay, it's going to be grow. The solid is, because it's no clay, right? So it's going to be grow. Okay. Okay. So, and then pro-eutectic, alpha solidifying. See, this is what I told you. A composition of alpha follows solidus. Composition of sternums is varies. Okay, from 40% to 61.9%. Right. And then all the remaining liquids are solidified. This one at the eutectic. Okay. So, and then if you reduce more for the cooling, okay, we lowers the alpha and also beta. The solubility lah is gonna be reduced. Okay. Any questions about this one? How it's going to be solidified? Okay, so let's see how we cooling at the hypoeutectic composition. Okay, so hypo is the left side. Actually, for this one, if we cooling the hypo, this one we call it this side. This one is actually if we divide reach with A, actually this side is a hypo. This one on the right side, we call it is a hypereutectic. Okay, later I will show you lah, because this one is more to alpha. Okay. There's alpha more here. This one is a beta. Okay. Okay. So when we slow cooling at hypoeutectic composition, this one hypoeutectic composition, right? This one, this side, this area. Okay. Primary alpha or pro-eutectic alpha phase is formed in the alpha plus L region, while the eutectic structure that includes layer of alpha and beta phase is formed upon closing the eutectic isotope, meaning that this side and also this side. This one we call it hypoeutectic. Okay, you have to know. Okay, result above TE, TE this one lah. TE we call it a eutectic line, eutectic point lah, above this TE. Growth of alpha solid alpha. Growth of the alpha solid phase. So meaning that if you get here that just above, okay, this one is alpha lah. Okay, and then at alpha stop growth. This one, this TE, TE is this this line. This line. This line. This line. It's stop growth. Proeutatic. Okay. And this one is growing. This one, this starting from here and this one to here. This one is above TE. Transfer to all this. Yeah, starting from E. Right here, that is starting from point E. Okay. So above TE, we call it just above TE. Just above TE, point D lah. Or just below E is point E. Okay. But above TE meaning that from this one lah. This area. This area. Okay. This is called alpha and liquid. Okay. Okay. So how about what we call it as a microstructure evolvement, okay, or development. So if you look at here, this one, point A, 100% liquid. Point C, right? That one is point C. Point B is much more smaller than point C lah, the proeutatic alpha. Look at here, that 24% of solid, right? And 76% of liquid. Okay. And then point D, see? Is growth. Okay, proeutatic alpha is growth. It's become bigger. It's become bigger. Okay, and the amount also increased. This one is 51, this one is 24. Okay, and then this one. Okay, proeutatic alpha. Okay, so we have proeutatic beta here. If you take beta, we just if you want to use color, you use color lah. That one is proeutatic, mostly for alpha because it's hypoeutatic. Okay, this one is hypoeutatic. The what is it? The here, okay, because this is beta. Okay, any questions before we move to the, or you want to 5 minutes, 10 minutes before we move? Okay, I just finish and then we break for 5 minutes. I just want to explain about the eutectic structure. Okay, for analysis, before analysis, and then we break for 5. Okay, let's see the eutectic structure. Okay, so this one, okay, there are various eutectic structure. This one is lamella. Okay, this is the growth direction. The arrow is growth direction. See, and then rod like, globular, circular. Okay. In eutectic reaction, both alpha and beta are formed simultaneously, resulting in the microstructure called eutectic structure. Okay. So in the lab, involve redistribution ion and the very eutectic reactions, we can have a various structure. This one, okay, a various structure. Look at here, in general, there's the four. Okay. This one is if we can using maybe like SEM microscope lah. We call it EM, FISEM. We can see this work lamella, rod-like, globular, and also circular lah. Okay. So structures depend on the factor like minimization of free energy, energy. Okay. So it's based on the growth of the nucleus lah. Okay. Affect the structure. Okay. And this one is the uh, uh, the most common okay. Is it okay? Hello? Is it okay now? Is it still lagging? Is it? No, it's okay. How about now? Okay. Okay. Okay, this is a general lah. And yeah, this is what I told you on the left side, this side, right? This is hypoeutectic. This one is hypereutectic. See, this is beta, beta, beta. Right, this one eutectic structure lah, alpha and beta. Alpha and beta. This one is a proeutectic. Proeutectic. This one proeutectic. Okay. And this one at the eutectic point. Eutectic structure. This one. This one is for sternum and lat. Okay. Just remember left and right. Okay. And then the microstructure involvement, if you look at here from the liquid, this one already explained, right? Okay. This one, the nucleus is growth, the solid, right? And then it's become bigger and become alpha and beta and also proeutectic. For this side, this one is beta, proeutectic beta, proeutectic beta. Okay. Above TE, growth of beta solid occur. Okay, this one is more to the left side lah, hypoeutectic. Okay, primary beta or proeutectic beta at TE. And then remaining liquid transform to eutectic structure. Similar like a hypoeutectic. Okay. Okay, any questions? Okay. Before we break for 5 minutes. What time we gonna finish? 10 o'clock, right? Okay, before we do the analysis. Okay, we break for 5 minutes. I also want to drink. Okay. Okay. We start again at 9:30. Okay. Okay, let's we resume. Okay, our lecture. We still maybe a very short before we finish. Okay. We will discuss on the phase diagram analysis, similarly like a binary isomorphous. I think we just discuss some examples, not all. I think there's too many sample problem here. I think including example is 1, 2, 3, 4, 5, 6. Okay, we just pick one examples or two examples. Okay, so we can do lah. Later you can do for the tutorials lah. Okay, for as exercise. Okay, so for your more understanding. Okay. Okay, so let's see the phase diagram analysis. Okay, if you look at here, that if we have a data 48% and of the sternum and 60% of plumbum or lat, okay, at 150 degrees C, we have to find the phase. Okay, what is phase is for this one, right? Okay, so if you look at here, that one, see, is moving 40%. Okay, so it should be alpha and beta lah. Here, this point. Okay, this one. because it's 40%, the initials weight, right? Okay. How about the phase compositions? Okay, if you see, since it's at 150 degrees C, right? 150 degrees C. So just draw the vertical line, right? This one, vertical line. Okay, that's the compositions, which is C alpha is equal to 11 weight% of stannum, and just extend this line. Okay, so since you make a vertical line here, right? Okay, to get the composition of stannum for the alpha, right? Okay, this is only for the alpha. Okay, so it's 11% of the stannum, right? And then for the beta, you have to extend to the right size until it touch the solver's line. Okay, so that we can get C beta, and then calculate. You can determines, or you can just read here is 99% of the stannum, and the rest is a plumber. Okay, how about the relative amount of each phase? Meaning that how many is alpha and how many percentage is beta. Okay, similarly also by using a level rules. Okay, if you look at here that W alpha, right? W alpha here. Okay, W alpha. Okay, S divided by R plus S. So meaning that what is it? C naught minus C alpha. Okay. Okay. So C naught minus C alpha divided by this one C beta lah. C beta minus with the C alpha lah. Okay. Sorry. We want S. Okay, sorry. So meaning that S is this one, right? So meaning that C beta lah. Okay, sorry. I just realized we have it. Okay. C beta minus C naught lah, so that we can get this area lah. Okay, divide by total area or total line. Okay, so that one. And then we can get 99 minus 40 and then 99 minus 11. Similar like this one isomorphous, right? 67%. And if you don't want to calculate W beta, not calculate, not using the equation. If you don't want to use the equation, just 100 minus 67. Okay, also is acceptable. So 33%. Okay, clear, right? So just remember the difference is on the, what is it? This one. This one is denominator, right? This one is what we call it? I forgot the top one. The bottom is denominator, I think. I don't know. I forgot. Okay. So just the difference is this one, S and R. Okay. Okay. So just you can calculate based on the level rule. Okay. This one also. For the phase at 220 degrees C, just draw the vertical and horizontal line. 220. So alpha and liquid. So how about the composition? See, vertical line, alpha, 70% stannum. This one, composition is the compound. Okay, the compound. Okay, the fraction is the phase. Fraction is the phase. Okay, we call it as a relative amount. Relative amount each phase. Okay, this one is the fraction for each phase. See. So 46 minus 40 divided by 46 minus with the 17 lah. Okay, this one for alpha, and 100% 21, you can get 79%. Okay, so meaning that is alpha and liquid. This one alpha and liquid, okay, because the phase is liquid and alpha. The previous one is this one liquid, it touch alpha and beta. This is in the phase of alpha and beta. So it should be alpha and beta. Okay, not with the liquid. Okay, just see the difference. Okay. Okay, how about the microstructure development? How can we calculate if we want to find the data is just above TE or just below TE, right? What's the meaning of just below and just above? Okay, so if you can hear that just above and just below TE, right? Okay, if you look at here, just above and just below this one, just above this one. This one is just above. Still touch the, what is it, what we call it as a eutectic point, just above. Okay, this one is just above eutectic point, just below this point. Okay, this one is just below. Same lah, this one. This one. This is just below. Okay, not too far. Macam kalau you have this finger, right, just above the finger, right, that you touch, still touch the your you have a, what is it, a pointing finger, right? You like this at the top, the pointing finger, right, like a horizontal line, just above this your pointing finger, you touch this above and below the your pointing finger, right? Okay, just make it a straight your pointing finger. Okay, so something like that. Okay. If just above and just below, if you look at here, how can we calculate C alpha and liquid? Right. If you look at here, that just above, right? So C alpha, you just extend here. This one, here, still the same. Because it's very, very small difference. So the percentage is the same, C alpha, with the eutectic point. Okay, so it's going to be 18.3. And then you extend to the right side. Right, this one. Okay, this one. And this one. Okay, so you can get alpha and beta. Still touch alpha and beta. This one, this is the solidus line. Sorry, this one no lah, it should be touch liquid lah. Sorry, okay, because it's just above. Okay, so this one lah. Okay, just above. Okay, if just below, alpha and beta. Okay, this one. Okay, so if you calculate alpha and beta, this is a microstructure development. Okay, okay, this is just below. Okay, if you do microstructure development, right, see just above still have liquid and solid. This one is become a 100% of a solid, alpha and beta, and also they have a pre-eutectic because this is a hypoeutectic region. This one hypereutectic region. This one is have a primary beta. This one is primary alpha. Primary is proeutectic. Okay, how can we calculate this one? See, just above TE, this point, the blue and green, right? This one. And you can calculate alpha and liquid, and also the fraction of alpha and liquid. Okay, and similarly also you can do for just below this line. Okay, so if you look at here, blue and brown, right? So just calculate that has alpha and beta because it's become solid. So the solid, what if use L and beta side? Similarly, if you use beta L side, hypereutectic, right? We have that example or not? Okay, we don't have, I think. Okay, page one. Notor, for above TE, what if I use L and beta side? Okay, for example, this one, right? Because we start with the 40% of sternum. Okay, if 40% sternum, meaning that is just above is between liquid and alpha. Okay, if you use the initial weight or concentration or composition is, for example, okay, this is for example 80% of sternum, right? If 80% sternum, of course in hypereutectic beta. Okay, hypereutectic area, hypereutectic. So meaning that, so this one just above, right? Just above. It's depending on the initial, okay, initial composition. See, this one. See the initial composition first. This one liquid and beta, just above liquid and beta. So this one, you change now. This one is for the beta. This one is for beta, right? For just below is the same. Just below is the same. Okay, just below meaning that you have to find C alpha and C beta. Okay, just below. Okay, it's the same. Okay, because it's alpha and beta, right? Okay, the same. Meaning that the composition is going to be to this side, to this side, this side, and also that side. You bring here and bring here. Right. Okay. Okay. Only the, above TE. Above TE, you have to change this one. Okay. And of course, WA and W beta is going to be different. C alpha, I think also, and beta also different because you're starting with the percent this one. Okay, you have to minus, right? Basically using a level rules. Okay. This one. What I mean by same is how you measure this one for alpha and beta. Okay, but to calculate C alpha and beta, the amount is going to be different. The amount because you start with the 80% of a standard. Okay, faham eh? Is it okay? Okay, right? Okay. Okay, so is it clear? We have the same actually. This one is for Argentum. I don't think we're going to discuss this one. I think it's the same. Similar this one. You just follow the what is the phase present there. Okay, chemical composition, amount of each phase, and sketch the microstructure. This is the answer already. Okay, liquid at 1000. And this one at 1000 because it start with the 71% of a copper. So meaning that here until 1000, right? This one liquid lah. Right. This one is gonna be liquid. Easy, easy. This one is just a minute. I don't want to repeat. Only the difference is the composition. Okay, 1000. Is it okay? I have a internet problem. Is it now? The line is okay? You can hear clearly? I just got a notification. My line is not good. If lagging, tell me, okay? What else? Yeah, C not lah. This one. Because only one, the chemical composition, right? This one, right? So meaning that your liquid, this one because Cl, right? Cl is going to be C not. Equal to how many percent? 75%. Okay, what else? Amount of each phase. This one is WL. WL. Because 100% is liquid, so equal to 100 lah. Right? Okay, 100%. Catch the microstructure. Microstructure just like this lah. Liquid. 100% liquid, okay? You have to write, okay? Don't just use L. Okay, this one is because difficult for me to write in the, how is it? Using this mouse. Okay, how about 800? 800, if 800, just roll lah, 800. Wait until 800, this one. Same lah. This is, so if you look at here, right? Actually, this one. Sorry, maybe my graph is not really this one. It should be, how to say, two phase alpha plus N, this one actually. This one here. To this side lah, more to this side. Okay, my graph is not good. If the real graph is touch this one. Is it? This one is L plus alpha lah for 800 degrees. Okay, for 800 degrees. Okay, amount HA phase WA lah. W alpha and WL. The microstructure, you just draw here lah. For 800 degrees, right? They have a microstructure development. Right? That one. So this one is you, what is it? Not as a pro-eutectic, pro-eutectic. You write pro-eutectic, okay? Alpha, and this one is liquid. Liquid. Okay, how much percent? Okay. Okay. So, and the next is, this one is a symbol, delta T plus delta is just above, okay? Just above. This one is just below. Okay. So, meaning that this one, right? Just above this line. This line. Okay. Just above this line. Just above this line. And also just below this line. So just make it very, very close because it's just above. Should be touch macam tu lah. Okay. So just above, if you look at there, L out. This one is space is L plus. Let's make it that lah, just to differentiate. L plus alpha lah. And then chemical compositions, WL. You know, this one is liquid lah, liquid and alpha. How much? How much argentum? Argentum for the liquid. How much argentum for the alpha? So just read from here, right? This one and also this one. You can read here. So liquid and alpha. And then compositions, you calculate W alpha and WL. Amount each phase alpha. This one is phase relative. Okay, and then microstructure become bigger lah. It's more bigger than this one. Okay, so meaning that you just draw, make it bigger lah. Okay, the pro-eutectic. Okay, this one pro. You have to write pro-eutectic, not only eutectic alpha. Eutectic is different. Eutectic alpha is here. Okay, pro-eutectic because it's a primary. Still have a primary here. Okay, this one is solid. And this one is a liquid. Okay, this one pro-eutectic alpha. Okay, and below, below similar, right? And pula. Jalan. Tiba-tiba hang. It's not moving. I got problem with the. Okay, now it's okay. Okay, so just below, just now, okay, similarly, just below is alpha and alpha lah here. Okay, just below here, right? Okay, this is just below lah, right? Just below, so the composition is one lah. Beta and liquid, alpha. Alpha, how many argentum? And beta lah. So, how many percent? Okay. And then you calculate lah. Find you hang lagi. Sekejap hang lah. I don't know what happened. Okay. So this one is alpha and beta here lah, composition. Phase W alpha and W beta lah. Okay. For the microstructure development for this one, okay, for this one, okay. So it should be you have to draw like this lah. We have a protectic protectic. Where this starting from 75 here, right? Super 75, this one 80, 70, 75. So 75 is going to be, just now is we define as liquid plus alpha, right? Okay, because of my graph. So if you look at here, there's microstructure, and then we have you just draw like this. Okay. This one, draw. You can see my slide, right? And then use the color, different color to differentiate eutectic alpha and eutectic beta. Hang lagi. Not moving, okay. You use color lah. This one is eutectic alpha and eutectic beta. The construction pula rumah saya. Sorry. This one eutectic alpha lah. This one is pro-eutectic. Pro-eutectic alpha. Okay. Okay. So that's all. Any question? And the rest you can read. The solution is there. Some noisy outside, so we cannot. I don't think I can give a lecture. So noisy. Any questions? I understand. Okay. So if